We're in for a special treat today. We have three speakers, all of whom are OPR affiliates, as well as members of the SPIA faculty. They'll each present a short talk, about 10 minutes, on some aspect of their research. And I hope to have substantial time at the end for a Q&A with all three presenters together for the Q&A. So that I don't use up valuable time, I'm going to give a very short description of each of the speakers right now. So our first speaker will be Filiz Garip, Professor of Sociology and Public Affairs. Filiz's research is at the intersection of migration, economic sociology, and inequality. She examines the mechanisms that enable or constrain mobility and lead to different degrees of social and economic inequality. She also focuses on how we learn from data, emphasizing the need to use multiple types of data and analytic strategies, and employing machine learning techniques when appropriate. Our second speaker is Bryan Grenfell, who is the Catherine Breiger and Sarah Fenton Professor of Ecology and Public Affairs. Bryan is a population biologist who uses both theoretical models and empirical data to investigate the population dynamics of infectious diseases, focusing on their epidemiological and evolutionary dynamics and control by vaccination. He considers a range of pathogens, including COVID, measles, HIV, and influenza, among others. Our final speaker is Arun Hendi, Assistant Professor of Sociology and Public Affairs. Arun uses demographic methods to study socioeconomic and racial inequalities in life expectancy and health, changing trends in marriage, divorce, and assortative mating, and population dynamics in cities and rural areas. His current projects include an examination of how and why Black life expectancy in the US improved over the last quarter of a century, and an analysis of how population flows between urban, suburban, and rural areas influence health and well-being. Filiz Garip will begin with her talk entitled Climate Change, Migration, and Inequality. The floor is yours, Filiz.
Thank you, Noreen. Let's see. Well, thank you very much. So I'm going to tell you a little bit about a recent project that I'm working, and I'm going to provide a high-level summary of a couple of papers that we're working on as a team. So the project is trying to understand how environmental factors shape human migration. And our team consists of economists and environmental scientists. I'm a former engineer and a sociologist by training. And this project, like Noreen said, is using a variety of different methods and kinds of data in order to understand this link. So our case is Mexico-US migration, the largest international flow in the world. And this solid line is showing the number of Mexican-born people in the United States. As late as 1980s, there were about 2 million Mexican-born in the United States. By 2012, the number had reached 12 million. And we estimated that at about half of that population was undocumented. So to give you a little bit of a background of this, the historical linkages of this flow go to early 1900s. This is when rail lines started to connect big cities in the central west of Mexico to the Texas border, and recruiters started using these lines to go and bring workers to the United States. And by 2014, by 2042, by 1942, actually employers no longer needed to make the trip because the temporary labor arrangement known as the Bracero program made this a formal labor arrangement. And then following next 20 years, about 5 million Mexican workers came to the United States as part of this program. So these initial events basically laid the foundations for migrant networks that connected people in Mexico to migrants to the United States. And these networks over time continued to transmit information and norms that made migration more likely and eventually path dependent. And of course, migration continued to make sense because of economic differentials. Even more recent analyses show that you can easily double your wage at almost kind of every education level, taking into account cost of living differences by crossing the border. So what about environmental factors? So this is the question that we're focusing on here. And the research in this area typically looks at weather fluctuations, gradual changes in rainfall and precipitation. We're doing the same here. And when we look at the existing literature, the results are quite mixed. So what we're trying to do with a series of papers here is to come up with a more credible identification strategies, to come up with more consistent results. And for that, we need to take a number of steps. First, we need to use highly granular data, both on migration choices and weather. Then the big challenge is how to pick the right weather measures among, almost an infinite number of choices. And then the third challenge is how to think about different mechanisms connecting weather to human mobility. We also want to consider potential intensification or decaying of effects. So for example, imagine there's a drought in a community. If there's an irrigation system, you might not immediately see an effect. But if the drought continues over multiple years, maybe the water runs out and you suddenly see an impact. This is what we mean by intensification. The opposite scenario is also plausible. As communities experience these shocks, they might adapt, divest from, let's say, agriculture, and then we might no longer see the weather impact. So we want to be cognizant of such possibilities. We also want to study heterogeneity in effects, which segments of the population are most responsive to these shocks. And then we also want to think about it in the broader context of the two countries, think about changing trade and migration policies over the years. So the data set that we use, the main data set, comes from the Mexican Migration Project, spearheaded by very own Doug Massey and Jorge Durand in Mexico. And currently, this data set includes about 140,000 individuals, and about 20,000 of them have migrated to the US at least once. These individuals reside in 170 communities spread all across Mexico, and we have annual information on their migration trips between 1980 and 2019. And this gives us over 2 million person years to work with. So we take this data and we merge it with weather information from NASA, and we use the finest or the highest resolution available to us. We take daily information on every kilometer square on Earth. So we take the communities in the MMP data, the community boundaries, and then we aggregate the weather within those grids within the community boundary. Now, this is an important point, actually. We spent a lot of time on the data merger issue, and we realized that the level of resolution really makes a huge difference. Just to show you one example, this Mexican map is showing you the number of days over 30 degrees in each state in a year. And the data comes from year 2000, but we're comparing each state to the number of days it experienced between 1980 and 1984. So we're treating that period as a normal. We're looking at the difference, and we're showing you the results in terms of standard deviations. Basically, how much hotter it was in 2000 compared to this previous period in standard deviations. And yellow and orange colors here indicate it was hotter than normal. And here we see that most states have experienced that, but there is not so much of a variation. Then we reproduce this at the municipality level, so higher resolution, and suddenly we see a lot more variation. And we actually see that some communities in this middle part have experienced extreme heat, but because they were distributed across states, the averages did not reflect that. So the communities we use actually are a lot smaller than municipalities. So it's kind of harder to show on a map. But we found that the results actually change quite a bit, and the results based on the state or municipality level data in the literature can actually be misleading. So this measure that we're using of extreme heat is only one. How do we go about choosing the potential measures to model in our data? So we go about it in a couple of ways. First, we use a data-driven choice. So basically, we use machine learning to pick the most predictive measures in this setting. So the output that we're trying to predict is first US trip. And then the inputs are, individual and household level characteristics, community level attributes, as well as many, many weather measures captured at various lags over time. So we're being agnostic about, what lag the impacts would occur, what measures would prove to be most predictive. And then, here I'm showing you the inputs by their degree of predictive power. And we see that the ones in yellow are the weather measures that consistently outperform others. And some of these measures are highly specialized and customized, like growing degree days, capture the weather that is optimal for crop growth, and the crop here is corn. So that's a customized measure, clearly capturing this agricultural mechanism. But we also have some generic measures, like the warmest night or the coldest day at various lags. Another important thing to pay attention to is basically the weather impacts actually pale in comparison to the impact of trade and visa, basically US visa accessibility. So then we also think about how about we come up with measures based on the particular mechanisms that we have in mind. And we here consider weather sensitivity to different crops, and we focus on corn here. We look at particular seasons of corn and measure weather in these periods. And then we write basically a straightforward model with various indicators. And here's what we find. We find that extreme decline in rainfall actually increases the odds of US migration, but rainfall deficits during this corn growing season matter the most. So the more we hone in on the mechanism, the better the signal becomes, and the effects are largest in communities without irrigation. And we also observe intensification effects. So we see that the effects are a lot higher when we have dry or very dry weather in sequence. And then we also find that these effects vary by household wealth. So basically, rich households respond immediately after 1 year of an adverse shock, but then poor households wait for consecutive or worsening shocks. So this means that if we wanted to intervene here, we could either intervene after 1 year of adversity, or we could invest in irrigation. And then we also collect some on-the-ground information. We did some field work in Mexico, and we spoke to farmers about what matters to them. And this farmer here gives us an example. He talks about how weather now comes in different combinations. So it's not just kind of temperature and rainfall, but how these combine. And when we refine our model based on these insights, we see that the farmer is actually right. When drought is combined with extreme heat, the signal is a lot higher. Now, two extensions that we're working on, we're looking at how weather impacts the routes that migrants are coming to the United States. And we see that weather matters, but not as much as the disruptions caused by NAFTA or kind of where border enforcement focuses. And basically, the main takeaway here is that we find that poor migrants choose locations where there's a low chance of apprehension, but a high risk of dying due to natural causes. And finally, we're looking at how extreme weather affects duration of migrants once they're here. So we look at undocumented migrants, and we see that extreme weather conditions back in their communities are making them stay a lot longer. So the main takeaways are migration is clearly a strategy, an adaptation strategy to weather shocks, but then rich households have an advantage. They can resort to it much quickly and more safely. They can actually hire smugglers to go through safer locations. And we see that migration and trade policies that US is part of actually can exacerbate the adverse effects of climate change. So I'll just acknowledge our funders and thank you.
Thank you very much. I got a lot of information in there, so that's great. So our next speaker is Bryan, and his presentation is entitled Medium-Term Epidemiological Impact of Mass Squaring, and he will be using a Blackboard, so you may want to make sure you're on speaker view. Bryan, it's yours.
Hold on a second. Can you see that?
Yes, good.
Okay, thanks. It's great to be here. Always a wonderful group to talk to. So we, and this is Jess Metcalf and Simon and Levin and I and our groups, and great collaborations on the climate front with Gabe Vecchi and geosciences, like all the epidemiological community, have turned our attention to obviously many things about the pandemic. Folks on this call have, I know, as well, and it's been all the way from what should Princeton University do to some quite applied things about estimating mortality rates and so on, to bigger things about uncertainties of immunity and the effect of climate drivers. But I want to focus just on one piece of it this time, which is the impact of COVID-19 non-pharmaceutical interventions on other endemic infections. And we've all seen this, that really there wasn't a flu season very much last year. There wasn't a season of, for those with very young children, respiratory syncytial virus, which is a very important disease of young children, RSV. So what are the longer term implications of that? And first of all, it's good to distinguish pandemics, which is this new thing where everyone is susceptible and therefore there's a huge epidemic, and we're in the middle of one now, and endemic infections. This is measles, and this is for the many demography buffs on the call. Measles was a biennial cycle before vaccination in the UK. It's an annual cycle, and this is a model fitted to data. It's an annual cycle when the baby boom happened, because susceptible recruitment perturbed this long-term attractor, and it's perturbations of these long-term endemic patterns that we're talking about here. So this is lovely work by postdoc Rachel Baker and grad student Daniel Park and other people looking at respiratory syncytial virus, which is, we can kind of think of as you're susceptible, you're infected, and then you're kind of immune for a good while after that. So it's a standard sort of SIR model. That would have been mysterious before the pandemic, but a lot of people have heard of that by now. And compared to the dots, which are what you'd see in a normal season, mask wearing in particular probably knocked down a lot of these infections and knocked them down to much lower levels in many contexts than you'd see. So what Rachel and Daniel and colleagues, is project this forward. We can make quite good models. Here's a model fit using state space approaches to the previous dynamics, and here are the susceptible patterns that are kind of complementary. Here's an example of the duration of mask wearing. You see there's a big susceptible buildup because the cases have dropped a lot. So when you relax the control, there's a big epidemic, and it's often out of phase. RSV is a winter infection. It's often a summer infection, and there's parallel work Rachel did with influenza on this. So you see that there are these big perturbative effects. So the question is, what's going to happen in the longer term? And here's just an update of that model for a couple of states, showing that again you can get quite good fits to the overall pattern. So it was a reasonably good out of sample qualitative prediction. So what I'm briefly going to talk about here is very interesting work. One of the great things for my field as a spin-off of at least in terms of trying to understand this terrible pandemic, has been, there's long been, would have been good to work much more with fluid dynamics people and so on, to think about transmission and how mask wearing and other things affect it, or air conditioning and so on. And that's brought up the idea that why don't we wear masks long term, particularly in the winters, to see if we can forfend other epidemics, if this seems to work so well. So this is just unpublished work that Rachel and another grad student, Shadi Sadroy, and I've been doing. So here's a typical RSV model. It's a high R0, high transmission rate infection. You introduce a period of control. There's a big epidemic when you get rid of let's say the mask wearing here, but let's say we permanently put on a reduction in the transmission rate. So what happens is that there's a long gap for the susceptibles to build up again. They build up to high levels, and then you get a series of recurrent epidemics. So it's settled to its new steady state. But you see that the new steady state isn't that different from the old steady state. So what's going on? What I'm going to do now is I'm going to unshare the screen. Let me just in-show first. So can people see me writ large now with the blackboard?
Yeah.
So you saw in that previous slide that what happens is the susceptibles tend to build up a lot, and then the system settles to a new state, and the susceptibles are very high. And what we can do is we can take the SIR model, and Noreen lectures brilliantly about this, so she can explain it all. We can look at the long-term dynamical behavior around these fluctuations, throw away the seasonality and so on. There's lots of complexities. We can look at the long-term equilibrium, and if we do that, then those effects are pretty laid bare. Here's the transmission rate, and we're reducing the transmission rate with masks and so on. If the R0 is very high to start with, then and as you reduce transmission rate, you don't have much effect on the infected average infected numbers. You will a bit more on the dynamic, on the nonlinear dynamics. You don't have much of an effect, but the susceptibles will tend to build up, so there'll be more susceptible people in the population. So you are lowering the transmission rate, but the susceptibles are increasing, and the effective reproduction ratio is the product of those two. On the other hand, for something like influenza, where you've got a low R0, you could really have a spectacular effect of mask wearing. So, overall, what we see is a mixture of high and low transmission infections. Influenza is definitely a bit lower transmission, so we might expect to see a stronger effect on influenza. So I'm just going to jump back to the slides now.
You have about 3 minutes.
Okay, this is good. Okay, so I'm going to do it on the board. So the conclusion is there, if you have low R0 infections, it's certainly really good to mask wearing would be very effective. If transmission rates are very high, you may see subtler effects. However, and there was a slide on this, if I vaccinate as well as mask wearing, vaccination will reduce the cases down like this. So a combination of vaccination and mask wearing, which is obviously a very virtuous combination, I'm sure many of us think, will be particularly effective in controlling the pandemic. One cri de coeur here is we tend empirically to measure the cases, but we much less measure the patterns of susceptibility, which one can do for by taking blood samples and doing serological studies. And this is something that Jess Metcalfe has pioneered, this idea of a global immunological observatory. If we had that, we could characterize these patterns very much better. Okay, so my PowerPoint presentation hung up, so I'll leave it there.
Okay, thank you. And I love to see people use blackboards. As I just told my class yesterday, I was missing the disappearance of chalk from our lives. Okay, so our final presentation will be Arun Hendi, and his presentation is entitled Immigrant Health and the Duality of Risk. And when that is done, we will take questions in the chat for all three speakers. It's yours, Arun.
Sure, thank you. Okay, can you see my slides?
Yep.
Okay, great. Today I'd like to talk to you about the contribution that immigrants make to the health of our national population. And towards the end of the talk, well, actually, I'll save that part for Q&A. So originally I was going to talk to you a bit about risk and a new risk, theoretical risk model that I'm developing. I'm going to save that for Q&A for time. Okay. Okay, so the motivating question in much of my recent work has been, what are the causes and social trends that have led to the recent mortality stagnation in the United States? In a 2018 paper in the BMJ, Jessica Ho and I showed that US life expectancy had begun to stagnate, and that in fact, the US hadn't experienced any significant improvements in life expectancy since 2010. In the modern era, the US has always done poorly in terms of life expectancy relative to its high-income peer countries. But the last decade represents an aberration, really a fundamental shift, where we're not only at the bottom of the pack, but we're not even really part of the pack anymore. The rest of the developed world has moved on without us, opening up a chasm in life expectancy between the US and the next worst country. This also represents a break from past long-term trends. So while the US in the past generally was near the bottom and experienced sort of a constant rate of improvement, that was roughly on par with some of the worst performing countries. That's not the case anymore. We're not really making improvement. So what we know, so we know that much of this poor performance is related to adverse behavioral trends among Americans, especially the sharp rise in drug overdose mortality. Much of it is related to slowdowns in the rate of improvement in cardiovascular disease mortality as well. So what I wanted to know is, if the country as a whole is doing really poorly, is that poor performance also reflected in trends among immigrants? And my hypothesis was initially that, probably not. And I thought that immigrants may in fact be bolstering US life expectancy, even as the native-born population continues to deteriorate. So the mere presence of immigrants may be masking even more adverse trends than what we had previously understood. So my co-author and I jumped into some of the data to examine precisely what the contribution of immigration is to the rate of improvement in US life expectancy. So these graphs show, for men and women separately, the ratio of US-born to foreign-born mortality rates by age. And you can see very clearly that US-born men tend to have significantly higher mortality than foreign-born men. For men in the year 1990, the ratio peaked at around 1.4, and for women, it peaked at around 1.5. So US-born men had mortality rates that were around 40% higher than foreign-born men, and US-born women had mortality rates that were about 50% higher than foreign-born women. So that was the situation in 1990, and by 2000, the inequality had grown even more extreme, as it did in each subsequent period. All the way through 2017, when the mortality ratio peaked at 2.5 for men and 2.9 for women. So what we're seeing is that the difference between the US-born and foreign-born in terms of their mortality rates has tremendously increased over the last 3 decades. And this growing inequality isn't just the result of a one-off increase or some hyper-recent phenomenon. It's not just drug overdose. It's a bunch of different things, and it's developed gradually. It's unfolded gradually year over year. So if you were to show a demographer the mortality schedules of the US-born and the foreign-born today without telling them what 2 populations those schedules correspond to, they might tell you that one of them corresponds to the national population of Japan, and the other one corresponds to the national population of Ecuador. Not in their wildest dreams would they guess that these 2 populations are actually living in the same country. The fact that the United States supports 2 such vastly different mortality schedules is shocking, and I think problematic for our theorization about why mortality is so high in the US. So let's connect these mortality ratios back to life expectancies because they're a little more interpretable. And you'll see here that if you look at the difference between foreign-born and US-born men, for example, we find a 6.5-year gap in life expectancy in 2017. And that's significantly larger than the life expectancy gap between the US-born and foreign-born that prevailed in 1990. We see a very similar story for women. Okay. So there's this large and growing gap, and the immigrant-non-immigrant gap in life expectancy is largely the result of adverse trends at the prime adult ages. So that's what we're finding, that it's coming from these prime adult ages of 25 to 64. It's not infant and child mortality that's driving these gaps. It's not mortality among older adults. For women, over half of the gap, close to 60% of the gap, is attributable to excess mortality at ages 25 to 64. And for men, that number is closer to 2/3. So in other words, at these prime adult ages, these working ages, that's where immigrants are really picking up a lot of additional life expectancy. And that's where the native-born, the US-born are losing a lot of years of life. So as an aside, I do want to point out that because of our ongoing and worsening drug epidemic, which is killing a lot of people at these working ages, immigrants are effectively adding to the number of person years lived in the country at the working ages, which is likely beneficial for our economy. And again, it's probably helping to prop up the labor market. Okay, so far I've made comparisons between immigrants and the US-born, but the US-born consists of a very heterogeneous population. And one dimension of heterogeneity is that it contains people whose families have been in this country for generations. And then it contains people like me, whose parents came to this country, immigrated to this country more recently. So if we want to think about the effects of recent immigration, it might make sense to consider not only the effect of immigrants, but also the effect of the second generation. And one way to do that is to remove both immigrants and the second generation from the population so that we're focusing only on people whose families have been here for many generations, multiple generations. And for lack of a better term, I'm going to call those people the US origin population. If you focus only on the US origin population, they're doing even worse than the US born population as a whole. Just how much worse are they doing? Well, if you were to remove immigrants and their children from the population, then our national life expectancy would drop by about 1.4 or 1.5 years. So the main things we've learned from this analysis are that the foreign-born live very long lives. And in fact, they're so long-lived that foreign-born American men have a higher life expectancy than the world leaders in male life expectancy, which is Swiss men. Foreign-born American women have life expectancies that rival Japanese women, who are the world leaders in female life expectancy. Because of their very high life expectancies, immigrants are making outsized contributions to our national life expectancy. In fact, in the decade between 2007 and 2017, foreign-born men and women were responsible for 44% and 60% of national life expectancy improvements. Between 2010 and 2017, immigrants experienced gains, while the US-born experienced declines in life expectancy. Thus, nearly all of the post-2010 mortality stagnation is due to adverse trends among the US-born. If we were to remove immigrants and their children from the population, our national life expectancy in 2017 would be reduced back to its 2003 levels. Now, to remind you what 2003 looked like, many of you were getting your first cell phones. There were still smoking sections in some restaurants, and Beyonce had just released her debut solo album. So in summary, immigrants bolster US life expectancy, and they've prevented our life expectancy stagnation from turning into a sharp decline. So I want to end this talk by emphasizing why this research is important at this moment. And there are many different reasons why this work is important at this moment. Some are political, some are policy, and others are related to scholarly concerns. On the political side of things, immigrants have been and will continue to be for the foreseeable future under attack. This latest line of attack is that immigrants are unhealthy people who bring disease and squalor to the country, or they're moochers who don't contribute to the country. There have been reams written on the contribution of US immigrants to the US economy and to the US polity. So what this work adds is that immigrants are not unhealthy people who are bringing disease and squalor to the country. Immigrants are actually boosting our life expectancy. And not only are they boosting it, but they're boosting it at the right ages. They're boosting it at the ages where we, the native-born people, are doing really poorly. Immigrants are supporting life expectancy at those key working ages and key reproductive ages where it's really important for us to have low mortality. But political considerations aside, political considerations should rarely have a place in academic presentation. But what I want to highlight is that the other big reason that this work is important is that it's immigrants and their children who are making up a growing proportion of the US population. They're clearly, so right now they make up around 15% of the population, and they're clearly having these outsized impacts on mortality trends and on our population dynamics. So if we want to understand American mortality, we need to understand immigrant mortality, because that's the future.